Hey, so welcome everybody. My name is Dr. Lauren Knightsky-Adamo. I'm one of the co-directors of the Rutgers Geology Museum, and I welcome all of you to our second presentation in our brand new Ask a Geologist web streaming series. So today I'm very happy to introduce one of my friends, Dr. Christopher Lepre, he will be talking to you all about the Earth's magnetic field today. Excuse me. So if you have any questions, please post them in the chat room on the WebEx link. And and please keep your microphones muted. We'll mute you guys from the administrative end as well. But place your questions in the chat room, and Dr. Lepre will get to them at the end of his presentation. So Dr. Lepre, he studied anthropology at Rutgers University for his PhD, and now he is a assistant teaching professor in the Department of Earth and Planetary Sciences, also at Rutgers University. So please help me in welcoming Dr. Christopher Lepre. So it's all you, Chris.
Hi, everyone. Can you guys hear me out there okay? So I just wanted to say good afternoon first to start off with, and I want to thank everyone at the museum for putting this on and organizing this. So also I wanted to just remind everyone, as Lauren was saying, that this is a series that's going on. So if you go to your Google and you type in Rutgers Geology Museum, should be the first thing that comes up here, right? And click on that, and it'll take you to the home page, and you can see all the events down on the right-hand side here. And right now we're doing Ask Chris Magnetic Field. That's with me today. And then you can see here, you click on Ask a Geologist right here. You'll go to the full list, and you can see that the good people at the museum have a full schedule for us for the remainder of the semester. We had grad student Ria last week who did an excellent job, and this is going to go all the way until April 30th. So there's a lot of content up here if you're looking for something for your kids to do while they're at home. And again, thanks to Lauren and Patty and Julie and Ria setting this up, and of course, thanks to Matt, our IT guru, for putting the WebEx presentation together so that we can make it smoothly like this. All right. So let me get back to the presentation here. And all right, so let me just, this is a little learning as we're going right now, because this is the first time I've done this, and we're still trying to work out some of the bugs. So one of the things to keep in mind is that while I'm giving the presentation, I'm not going to be able to see the chat screen that well. So I may not be able to answer your questions in real time, but there's going to be time at the end, and I'll try to get to as many questions as I can. But as I'm going through it, I may not be able to see the screen where the chat questions come up. But maybe I'll check in periodically just to see what's going on in the chat. Okay. So let me get back to the presentation. Share my screen here. Go. All right. So this is Ask a Geologist. I'm a geologist, Dr. Lepre, and we're going to talk about the magnetic field today. But before we do that, we're going to talk just a little bit about myself, background information about a geologist. Okay. I study Earth's magnetic minerals and its magnetic field. Mostly, I use these minerals and the magnetic field to do things like determine how old fossils are. Sometimes I use the magnetic field and magnetic minerals to tell how old archaeological sites are. And also, a new aspect of my research that I'm getting into is talking about what was the climate like when dinosaurs roamed the Earth at about 210, 215 million years ago. And again, using magnetic minerals, a mineral called hematite, which we'll talk about a little later on in the lecture today, but a mineral called hematite, to use that to tell us what climate was like during the Triassic period when dinosaurs. And just a fun fact about myself, I grew up in New Jersey, and right now I live on the Orange Mountain, which is a 200 million year old lava flow in New Jersey. And that's in northern New Jersey. So I have to give a shout out to all my friends in Essex County, our people from the Brick City and Newark, New Jersey, our friends in East Orange and West Orange, and all the Oranges, friends in Caldwell, Montclair, and of course our friends from everyone that's listening and tuning in right now. Our friends in Piscataway, our students in East Brunswick and North Brunswick. So the whole viewing audience. But yeah, so the Orange Mountain is probably one of the more famous mountains in New Jersey. It's in Essex County, New Jersey, and it's a lava flow. It's lava that erupted 200 million years ago when tectonic plates were spreading, and it cooled, it chilled, and it formed solid rock, which many of us in northern New Jersey today. Okay. So let's get into the magnetic field now, and we can ask the question. We can start off by saying, well, why would a geologist study the magnetic field? Other than it's really interesting, it's really cool, and a lot of fun. What does it tell us about the Earth? And it tells us a number of things. And we're not going to have time to talk about everything it tells us about, but just this cartoon gives us an idea of some of the things we can look at. We can look at, for example, if we go over here, this is a cartoon of the interior of the Earth, and these swirl lines here, right? These arrows, these red arrows, swirl lines. This is a representation of how the magnetic field of Earth is generated at the Earth's core. So we can use magnetism and the rock preserved, or the magnetism preserved in rocks to understand Earth's core and its origins and how it changes over millions of years and maybe even billions of years. Earth formed over 4 billion years ago. We can study how the field, Earth's magnetic field, reverses itself, which is a process we'll talk about a little bit later on in the lecture. Tells us about how tectonic plates spread, how continents break up, how the sea floor spreads through time. And it also can give us ideas about how certain rocks form and are preserved within the interior of Earth. So there's a number of different things that we can get from this, and I only do a very small portion. Many types of scientists study the Earth and use magnetism. My focus is really just using it to as like a time scale or as like a ruler of time to determine how old Earth events are or how old fossils are, and also using the minerals to talk about past climate change. So I thought we'd start off by saying, what is the magnetic field of Earth? What is it? Well, there's many different phenomenon in our universe, many different phenomenon in the solar system. And one of the things that planets have, many planets, not all of them, but many planets have a magnetic field. And it's a force. It's a natural force. And our planet's magnetic field works like any other magnet. So if you look up here, there's this simple horseshoe magnet here, right? It has a north side and it has a south side, or a north pole and a south pole. And it attracts things like paper clips or nails or anything that has a magnetic type of metal, which is typically iron. Or our refrigerator magnet, right? Our magnetic field works just the same way as a refrigerator magnet. Very, very similar. Not exactly, but fundamentally it's the same. Except our magnetic field is very weak. It's about 50 microtesla. And Tesla is just a unit that we use to measure magnetic intensity or magnetic strength. Right? It's similar to kilometers for measuring distance or pounds for measuring weight. And there's a few different types of terms we can use, but 50 microtesla is about the strength of our magnetic field. Now, to put that in perspective, a refrigerator magnet, something that keeps your schoolwork on the refrigerator or your calendar on the refrigerator, is about 200 times stronger. One single magnet, right, is about 200 times stronger than our magnetic field. So it's not very strong, our magnetic field, right? And just to, sometimes I get the question, well, why don't computers or cars or something, made of metal that we have in our house get affected by the Earth's magnetic field? And that's because it's very weak. And to put that in a little bit of perspective, think about a compass. Right? A compass needle is really small, and our field is just strong enough in order to move around this small little compass needle. Right? It can't affect big things like bridges made of iron, or it can't affect big things like cars, but tiny little pieces of iron, like a magnetic needle on a compass, get affected by our field. And in fact, in rocks, many rocks that you see in New Jersey have tiny little minerals in them made of iron that act like a magnetic needle on a compass. And those tiny little minerals in rocks get forced, get moved around by Earth's magnetic field, much like we see in this cartoon of a compass here. Now, the study of the magnetic field is kind of ancient, in fact. We know that over 2,000 years ago, people in China were using compasses to observe the magnetic field, and it was a very simple principle. They had well, this is an actual representation. This is an actual compass that was used in China, right? And they would scribe in different words and symbols around it to represent the different directions. So if say that this would be north over here, right? And this would be south over here, right? Make up here east, right? And over here west, right? And they would have this spoon-like thing in the middle, and this spoon-like device here would be made of a material called lodestone, which we know today is the magnet, right? And it would spin around. The spoon would spin around, and it would detect Earth's magnetic field pointing towards north. It really wasn't until about the 1600s did people start, using math and physics to really understand what was going on with the magnetic field. And one of the first scientists to examine this was a man by the name of William Gilbert. And he's kind of credited with the first person to write down all the observations in an academic or scholarly textbook or a book kind of way about what our magnetic field was and how it works. And he's kind of credited with saying the magnetic field acts like a simple bar magnet that's centered around Earth's rotational axis. So we probably all know that Earth spins, rotates on its axis, which gives us day or night, and our magnetic field is centered around this axis of rotation. Another gentleman by the name of Edmund Halley, which you probably know from other types of scientific observations, most notably Halley's Comet, he was one of the first people to produce a navigation map based on the magnetic field of Earth. So the Chinese knew about the magnet or the Earth's magnetic field over 2,000 years ago, and a couple hundred years ago, scholars began to put this down in a more systematic way. So we've been studying Earth's magnetic field for a fairly long time. So moving on, we can ask the question, where does the magnetic field come from? How is it made, and where is it made on Earth? And well, as I said before, right, many planets have magnetic fields. In fact, our sun, our own sun, has a source of magnetism. It's a fairly common force in the universe. Right? Our universe has things like forces. Magnetism is one of them. Gravity would be another force. And then we have things like energy. Sunlight would be an example of energy. And then we have things like matter. You all know, like a solid, a liquid, a gas. And our planet manufactures these things. It has its own internal source of energy down at the Earth, or Earth's core here, right? The inner core right here. Right? This is the outer core here, and this is Earth's mantle, and this is Earth's crust. So energy is generated within the core here, and also the magnetic field is generated within the Earth's core. Specifically within this part here, this is the liquid outer core, right? So we have a solid inner core. Right? We have a solid inner core here, and this is largely made up of metal, mostly iron. It's got some cobalt, it's got some nickel in it, which are other types of metals. And then it has other things that aren't metal, but most of it, about 99% of it is mineral iron. And then we have this is the liquid outer core, which is mostly the same material that the inner core is made of, but except it's liquid. It's not a solid like the inner core. And then we have the mantle, which is largely rock, some molten rock, and a lot of solid rock, and then of course the place we live is crust. Well, it's this liquid portion of the core here at what we call the core mantle boundary, where the mantle, the bottom of the mantle and the top of the liquid core touch. That's where we think that the magnetic field is being generated. And so here's just a nice little cartoon or a nice little GIF of the interior of our Earth here, right? So as I was saying before, you have your inner core, your outer core, your mantle, and your crust. And on the diagram here, or the GIF here, this would be our inner core here, which is solid metal, iron. This part here would be the liquid outer core that's turning, that's convecting, that's moving around. There's a lot of sloshing going on as Earth spins on its axis, as Earth rotates. There's a revolution around the sun, right? So all this liquid outer core is sloshing around here. Sometimes some of this slosh gets spilled out into the mantle, and you get these things coming up called mantle plumes, and they come up to the surface of the Earth here, right? And they might cause volcanoes like we see with the islands of Hawaii, for example. And we think it's that this movement, right? This movement that's going on within the liquid outer core here, this is what's generating the magnetic field of Earth. In many ways, we think that this movement of the liquid outer core is acting just like a simple electrodynamo that humans make all the time to generate electricity. And right here, this is Hoover Dam. This is probably one of the most famous dams in the United States, if not the famous dam. And it's a hydroelectrical power plant, and it generates electricity from the water rushing down through the dam and being let out through the sluiceways here. And as the water comes through the dam and the sluiceways, it turns these generators that we see down here, right? And these generators, they turn and turn around, and they generate electrical field. And in a very similar way, electricity, I should say that electricity and magnetism are very closely related, because a lot of magnetism is based on electrons. And as you probably know, electrons are part of an atom, neutrons, protons, and electrons. So electricity and magnetism are closely linked because they're both based on electrons within atoms. And the Earth's inner part, its core, its liquid core, behaves very similar to one of these electric. Okay, so our magnetic field is generated within the interior of the Earth, right? It's generated by the liquid outer core, and it's not perfect. It's not like what you would see exactly with a bar magnet here. So on the right, you see a simple bar magnet, and you have a north side to the magnet and a south side to the magnet, and all these speckles that you see around here, these are iron filings, and they're just arranged in a way by the magnetic field of this bar magnet to illustrate the magnetic flow lines, right, that are coming from the north side and going back into the south side, swirling around. And this is a well-organized magnet, right? The flow lines are very symmetrical, meaning that they're equal on either side of the bar magnet and very systematic. Our planet, it's a very good magnet, or it has a very good magnetic field, but it's not as well organized as we see here, right? Because there's parts of the interior of our planet that aren't magnetic, that aren't made of iron. And so there's weaknesses and all these discontinuities, or meaning irregular parts within the interior of our planet that aren't really good for conducting the magnetic field. So it's not perfectly organized like you see with a bar magnet, but it's good enough to generate a great magnetic field. All right. So let's change gears here a little bit, and let's talk about how geologists study the magnetic field at the surface of the Earth. Because right now we've talked a lot about the interior of the Earth, and of course, as we go from the surface down to the interior, there's a lot of pressure that increases, and there's a lot of temperature that increases, and therefore it's not really good for people living down there, right? People can't get deep within the Earth. Not only are the temperature and the pressure wrong, but we just don't have the technology to drill that far down or to investigate that far down. So we have to do it remotely. We have to do it from the surface. Sometimes people do this using seismic waves, seismologists. They measure earthquakes, and they use the earthquake waves to determine what the interior of Earth looks like. But another way we can assess the magnetic field is by looking at minerals or materials that get affected by the magnetic field. For example, we see this is a very common magnetic mineral. This is called magnetite. And as the name kind of gives away, it's a very magnetic mineral. Excuse me. Magnetite is made up of the elements iron and oxygen. Right? So it's made up of Fe, which is the symbol for iron, and it's made up of oxygen. In fact, it's 3 atoms of iron and 4 atoms of oxygen. That makes the mineral magnetite. And when these atoms of iron and oxygen come together and bond in a certain way, they produce a very strong magnetic field, or a magnet for this mineral. In fact, magnetite is probably the strongest naturally occurring magnetic mineral that we have. There's some other mineral called hematite, which is similar, but probably magnetite is. Another magnetic mineral that we can talk about is the mineral hematite. And you've probably seen magnetite before, but I know you've definitely seen hematite before. Hematite's all over nature. Hematite also contains iron, 2 atoms of iron, has 3 atoms of oxygen, right? And again, these atoms of iron and oxygen, right? So this is the symbol for iron, Fe, and oxygen, O here, 2 atoms. And when iron and oxygen bond in this particular pattern here, it makes a magnet. It makes hematite behave like a magnet. Now, it's not as strong as magnetite for reasons that maybe we'll talk about later or not. They're a little bit more complicated, but magnetite's much stronger, and hematite behaves like a weaker magnet, but it's still a good magnet, and it can be used by us. We can find this at the surface of the Earth, and we can use this mineral to study how the magnetic field of our planet behaves. Specifically, there are all sorts of hematite-bearing rocks at the surface in New Jersey, and these are New Jersey's famous red beds. Excuse me while I take a sip of water. So you've probably seen these all over the state before. You've probably seen them in North Jersey, also Central Jersey. The southern limit is about New Brunswick, where Rutgers is. It might be a little bit further south, but by and large, they only incur from the central part of the state to the northern part of the state, red beds. And these are mostly Triassic and Jurassic age rocks, these red beds. And they're called red beds because they're red, and they get their red color from the rust that is naturally occurring hematite. So I think Sarah Alvarez might have had a question there that just popped up, I saw, and said, where can we find hematite? And I think the short answer, Sarah, is that you can find it everywhere, because everywhere likes to rust pretty much. So every time you see a red rock in New Jersey, think hematite. And these are some nice dinosaur footprints within these red beds here. These are from Clifton, New Jersey. And these are growliter tracks, which is a small theropod dinosaur. The dinosaur is called Coelophysis. And Coelophysis was one of the first bird-like dinosaurs that evolved. And we have a great record of their footprints in New Jersey. Someone just asked a question, I forgot the name. They said, where can we find red beds? Where can we visit a red bed? Well, this one you can, like I said, in Clifton, New Jersey. If you ever come down to Rutgers University in New Brunswick, if you walk around campus, you can see all sorts of red beds. By my house, for all my West Orange friends, if you ever get on the Parkway from 280, if you're going 280 east towards New York and you get on the Parkway there, look to the right next time, and you'll see a nice outcrop that looks very similar to this one over here. Not exactly, but similar of red beds, right? A nice example. I'm seeing I'm getting close to 229 right now, and I think I want to leave some time for questions at the end. I'm gonna hurry up here. Aaron Alvarez asked the question: are there any red beds in Virginia? Yes. The red beds, these Triassic, Jurassic red beds, they extend from all the ways north in Nova Scotia, all the ways down to the Carolinas. And like I said, there's Triassic and Jurassic, so they're about 200 million years old. You should be able to find them if you're from Virginia, and you should be able to find them maybe even in your own backyard. All right. So why is this important? Why is this information, other than it's totally fascinating, it's a lot of fun to study. You get to walk out into the outdoors. You get to go hiking around. You get to collect rocks. You get to use all sorts of cool scientific lab equipment like magnetometers and drills to drill out samples of red beds. There are some important reasons why we want to study this. And one of the things is that maybe you knew this, but Earth's magnetic field actually provides us with a layer of protection from harmful radiation being put out by the sun. We all know the sun is a great source of energy, and it shoots a lot of rays and energy out towards our planet. Some of these are good and very helpful, and other of these are a little bit too strong for humans to bear and other types of life. But our magnetic field acts like a filter and filters out some of these harmful rays of radiation. The other important thing that Earth's magnetic field does is that it protects our atmosphere from the solar winds. And the solar winds are, again, they're like these particles being shot out from the sun, and they're constantly barraging planets and moons and other bodies in our solar system. And what the solar wind can do very easily, if we didn't have a magnetic field, it could strip away our atmosphere. It could just take it right away because there's so strong of a barrage from solar wind. And of course, that wouldn't be good because we would have nothing to breathe. We would have nothing to keep us warm, right? Because the greenhouse effect is not greenhouse. A right amount of greenhouse effect is good for us, right? And so we need the atmosphere to do that. And the magnetosphere, or Earth's magnetic field, protects us from the solar wind. I just saw Hayden had a question. They said, do all planets have a magnetic field? That's a good question. Not all planets, but in our solar system, we think all the interior planets, or the rocky planets. So Mercury, Venus, Earth, Mars, these are called the interior or the rocky planets. That's because they're made of rock, and they have a core, a mantle, crust, just like Earth. And Mercury has an active magnetic field. Earth has an active magnetic field. Mars had a magnetic field, but it died out because its liquid outer core went solid. Moon had a magnetic field because it's like a small rocky planet. And then places like Jupiter. Jupiter has a magnetic field because it has a metallic hydrogen core. But it's not exactly the same as the rocky planet. So it's important to study the magnetic field because it protects us. It helps us. And one of the more interesting things about our field is that it reverses itself. And there's no real period to this. It does it kind of randomly. And we're not really sure why it does it and how often it does it. Well, we have a pretty good idea how often it does it. We're not really sure why a certain frequency at which it reverses itself happens. So on the left here, this is what today's magnetic field looks like. We call this a normal magnetic field, right? Because the north side of the field points down here, and the south side of the field is right here. So, so when you're pointing your compass and it points to the North Pole, it's actually pointing to the south side, or the negative side of our magnetic field. Now, if we were to turn back the clock, if we were to go back into a time machine to 800,000 years ago, we would see that the situation is reversed. We call this my handwriting. No spell check on. That's not the most neat handwriting here, but a reverse magnetic field. Maybe you get the picture. Okay. I'll try to improve my handwriting for next time. Anyway, a reverse magnetic field, meaning that the field has flipped. And now the north side of the Earth's magnetic field, right? And north is indicated on this diagram by the arrow pointing. So the north side is now pointing towards the North Pole, and the south side of the Earth's magnet is at the South Pole. So if you were to go back in time to 800,000 years ago and you were to have a compass in your hand, it wouldn't point to the North Pole. It would actually point to the South Pole, right? Because as you probably know, opposites attract. If you take two magnets of the similar polarity, meaning if they're both north magnets or they're both positive magnets, you try to stick together, they're not going to stick together. They're going to repel one another. In the same example, if you take two south magnets or two negative magnets, try to stick them together, they're not going to stick. They're going to repel, right? So if you take your compass your compass is actually pointing to the south side of Earth's magnetic field at the North Pole. If we went back in time 800,000 years ago, our same compass would point at the South Pole, the south side of the magnetic field of Earth. All right, so we're getting down to the wire here, and for my last slide here, we have kind of a little bit of complicated picture, but this is kind of what we know about Earth's magnetic field reversing itself. And on the left here, right, I'm going to throw out a big word here. This is called the geomagnetic polarity time scale. Okay, there's not going to be a test later, so you don't have to remember that, but I just thought I would throw it out there. Right? This is called the geomagnetic polarity time scale, and this is a record going back 5 million years, and the time scale goes back longer than 5 million years. We have time scales going back hundreds of millions of years back. This is just for the last 5 million years. And the black bars within the time scale represent periods of Earth's normal polarity, like we are today. And the white bars represent periods of reverse polarity, like the one at 800,000 years ago. And we give these different intervals. So like we live in the Bruns normal interval today, because our field is normal. And then if we go back in time to the Madhyama was actually a time between about 780,000 and 2.5 million years ago, when Earth's magnetic field was mostly reversed. It was mostly, as you can see, white here. But there was small intervals that were normal. Like right here around 2 million years ago, this is called the Old Divide, when we had a normal magnetic field. And also around here at 1 million years ago, we have something called the Jaramillo. And the Jaramillo was a period of normal magnetic polarity during the overall reverse Madhyama. And we can see these things in when we look at red beds, for example, in New Jersey. We can see these things if we look at lava rocks. And one of the first ways that geologists observed the flipping of the Earth's magnetic field was using the record of seafloor spreading that we see in the Earth's ocean. And from that, looking at the different magnetic polarities of the rocks at the bottom of the seafloor, not only did this help us understand how plate tectonics creates mountains and oceans and moves continents around, but also it gave us an idea about the intensity, the strength, and how the magnetic field changed. So I think that's all I have in terms of talking, and we can open it up to some questions. See if I can stop sharing here. Hopefully, see me again, and I guess I should. Oh, I got some questions sent to me by email, right? So we have a few email questions. Maybe we'll take a couple of those first. How about, right? So so Karen asked, for example, oh, this is a great question. In fact, do animals use the magnetic field to navigate, right? And the answer to that, and I'm sure Karen probably had a suspicion. Yes, the answer to that is definitely yes. In fact, if we could, let's go. Here am I? Go back to Firefox here. I'm going to show you something really cool, right? So you can do this at home. You can go to your Google, right? And you can Google magnetotactic bacteria. Ooh, right? And there's a picture of magnetotactic bacteria here, right? So this is about 5 microns scale here. So it's larger than 5 microns. You can think of a micron as being about 1,000 times smaller than a millimeter, right? And this is a bacteria, right, that we're seeing here. It looks kind of like a small worm or an inchworm. And all these little black dots inside, these are tiny crystals of the mineral magnetite, just like the one I showed you before in the presentation. And you can see these magnetite crystals line up almost perfectly in a straight line through the bacteria's body. And this little critter here, this microscopic piece of bacteria, it uses these magnetic crystals, these magnetite crystals, to navigate through water. It aligns itself to Earth's magnetic field. So bacteria do this. There's some evidence that birds also do this. And accidentally muted my mic there. And in fact, what we think is that probably there is some evidence that humans have magnetite in our brain, and we're not really certain why yet, but it maybe it has to do something with the navigation that we see in other animals. Let me see here. Any other questions? The most common mineral in New Jersey. That's a good question because New Jersey, just like everyone else, has a lot of minerals. I'd say, well, at Earth's surface, probably one of the most common minerals is quartz. Probably very similar in New Jersey. As I said before, hematite is really common because we have the red beds. And oh yeah, feldspar would be another really common mineral. If you ever go to a New Jersey beach or any beach, all the light-colored tiny pieces of sand that you see, usually they're quartz and feldspar. I'm going to scroll through these questions here. See. Oh, Kaylin Crowley has a question. Can magnetic rocks affect Earth's magnetic field? And the short answer to that is no. Not at the surface of the Earth. The surface has the rocks at the surface have very little influence on what's going on down deep or Aaron Alvarez asks, how does the magnetic field reverse itself? Does it happen every day? Well, the second part of that question we answered, so no, it doesn't happen every day. And we're not sure how often, why it decides to reverse itself. We think maybe it might have to do with, remember I talked about how things are moving around, sloshing around in the interior of the Earth? Well, maybe it might be that some of that sloshing gets moved around in a way that knocks the magnetic field off kilter for a little bit, and it has to reorganize itself. Sometimes it doesn't reorganize itself into a normal situation, but into a reverse. That's something that's an active field of research we're looking at. So, I think looking if there's any other questions here. Go on. We have about another 15 minutes. So let me see if there's no. Feel free to chat something.
Hey, Chris, you can go to the Google Doc that we of questions. There's we put a bunch in that one that you might have missed.
Oh, okay. Oh, let me see if I can refresh my Google Doc here. Okay. Thanks, Lauren. That's Dr. Lauren, everybody, who's one of the key people to put all this together. And I want to remind you to go to the Rutgers Geology Museum website to get the full list of speakers until April. If you want more of this good content that we're giving to you today. Okay, Google Doc. Oh wow, so a lot more questions. Ooh, wow, the questions really came in. Does lava come from the mantle? That's a great question. Lava, in fact, 100% does come from the mantle, right? So the mantle undergoes melting. It gets transformed into magma, which is liquid rock below the surface. And then, through a volcano or through a crack in the earth, that magma extrudes to the surface. And when it extrudes to the surface, we call it lava. How do tectonic plates move? Wow. You know what? That's a really great question. It's kind of a complicated one, and it's a little bit out of my area of expertise, but there's going to be plenty other speakers this semester. And I think, in fact, within the next week or two, I think one of our graduate students, Aiden, might be, oh no, Chris Rowan, one of our graduate students, Chris Rowan, who studies tectonics in Africa, in the country of Kenya, in fact, he's going to be talking about plate tectonics. So I think we're going to save that question for him. Look at some other good questions here. Oh, here's a question from Union, New Jersey. Hi, Union, New Jersey. Right. Are there any changes happening to Earth's magnetic field? What does the field do? How do you know? Those are all really great questions. And in fact, I'm going to answer the first one by saying yes. The magnetic field, in fact, magnetic north is constantly on the move. It's drifting. It's not perfectly centered at the North Pole, right? It's in the general vicinity of the North Pole, but it doesn't usually stay right at where the North Pole is. In fact, it moves around quite a bit. Sometimes it goes off into one direction. Maybe it might go 10 or 20 degrees west of the North Pole. Sometimes it goes east, right? So it's constantly in a state of motion because, as I said before, it's generated from the liquid part of the core, and that's in a state of motion. So all the motions that are going on with the liquid outer core, right? Usually, not all of them, but a number of them, especially if they're big enough, are being reflected at the surface of the Earth by the behavior of the magnetic field. More here. Oh, Caitlin again has some good questions here. Okay, does the outer core ever melt part of the inner core? That's a good question. I'm not really sure about that one. I'm sure there's probably some melting going on. I know there's exchange of elements that go on between the inner core and the outer core. So the inner core itself is actually moving a little bit side to side as the Earth rotates and as it revolves around the sun. So the inner core, the solid inner core, kind of like moves back and forth, almost like a pendulum on a clock. And as it moves back and forth, there's some melting that does go on, and that releases elements into the liquid outer core. Lava comes from, and that is, oh, Sebastian from Haymarket, Virginia writes in, and Sebastian says, how does the magnetic field affect us? That's a good question. That's still, again, one of these words that we like to use in science, like an active field of research. Scientists are hard at work trying to determine if the magnetic field has any kind of impact on our senses and to what extent it might. Right now, there's lots of experiments. Very famous magneticist called Joe Kirshevink at Caltech in California. He has a really big project. He has a really nice laboratory there where he's looking at people's brains and using all sorts of imaging techniques to understand the magnetic minerals that might be observed in the brain. Harmless magnetic minerals, right? Parts natural ones that our bodies make, and how these minerals might be related to the magnetic field and what sorts of relationship they might have to our senses. Okay, let's see if there's any. Can you talk about what would happen if Earth's magnetic field reversed? So Lillian writes, can you talk about what would happen if Earth's magnetic field reversed itself? Well, that's a good question, actually, because what we think when we look at geological records, when we try to read the rocks and see the record of Earth's magnetism trapped in the rocks, what we can see is that it takes maybe about 8,000 years for Earth to undergo a full reversal. So it's not just like an instantaneous process. It's pretty long, at least on human lifetime. Right? 8,000 years is a long time. So if you think about human civilization, 8,000 years ago was before the Great Pyramids in Egypt were built, before the great kingdoms of the Middle East were built. We're talking big time prehistoric times when people were not living in caves exclusively, but technology was certainly not advanced. It takes 8,000 years for a full reversal to happen. What would happen, some scientists think that a lot of the solar radiation that's harmful to us would be let in during this reversal and maybe affect life in a negative way on a temporary basis, not a long term. And maybe some of these animals that depend on Earth's magnetic field to navigate, like birds, for example, their migration patterns would be altered, would be screwed up during a reversal. The bottom line is we're not really certain because no one's lived through a reversal, and we can only speculate, and we're just starting to scratch the surface of evidence, of real hard evidence to understand how life might be affected during magnetic reversal. But you don't have anything to worry about. It doesn't seem that Earth's magnetic field is going to reverse anytime. So Anthony, I saw your question here from Somerset. Asked what causes the magnetic reversals to occur, and I think I answered that one already. Just don't want you to think I didn't see your question. Oh, Karen from Cherry Hill, New Jersey asked, how does a compass work and are they accurate? Well, they're very accurate, in fact. They're one of the most accurate ways that we can use to navigate because they don't rely on electricity. They don't rely on batteries, just rely on Earth's magnetic field. The trick is that magnetic north and geographic north are not always in the same place. So when you're navigating, you're not really navigating to what we call true north or geographic north. That would be at the very top north pole of Earth. And it depends on where you go on our planet, how different a magnet will indicate magnetic north from geographic north. So for example, if you go to Kenya, which is in East Africa, right, magnetic north and the geographic north will be off by a couple of degrees. But if you go to Colorado, for example, the difference between magnetic north and geographic north, from the perspective of your compass, you might have to correct your compass about 10 degrees. But as long as you know your correction factor, right, as long as you know you're in Colorado and that it's about 10 degrees off with your compass, then you can correct for that, and then it becomes a fairly accurate way to navigate around, especially if you're hiking through the beautiful Rocky Mountains. We got about 5 more minutes here, so I'm going to try to get to all your questions. And see here. Oh, I think that's pretty much all for the write-in questions. Let me just refresh this because I see that there's some more chat questions here. I just want to get to the Google Doc question before. All right, let me get to some of these before we end here. Kaylin Crowley again. Kaylin, thanks for all the good questions. I think these are the people from Virginia. If Earth has a magnetic field, why doesn't the moon crash into Earth? Does it have some kind of friction? Oh, that's a great question. Well, what I'll say is that there's 2 different forces that account for the Earth and the moon relationship, right? Or I should say, gravity accounts for the Earth and the moon's relationship, which is a different force from magnetism. And we're going to have, I think, later on in one of our future lecture series, right? I think Dr. Yuli Gross, who's an expert on the moon, is going to talk a little bit more about how the moon and the Earth relate to each other in terms of gravity. Uh, the magnetic field doesn't affect the moon, or at least we don't think it does, right? One, the moon's magnetic field died long ago because it's much smaller and its liquid outer core cooled much more rapidly than Earth, and therefore it doesn't generate its own magnetic field anymore. And two, Earth's magnetic field is very weak, as we talked about. It can only move a tiny little compass needle. It doesn't have the ability to move a planet or a moon, excuse me, a moon out of orbit. So that was a great question. So I think we're coming about. Oh, I see all the thank yous too. Well, thank you. You know, seeing all this thank yous, and so I think we're right about ready to sign off here. Dr. Lauren, what do you think? Are we done here? Should we keep it going for the next 3 minutes? You think
No,
of anything else?
I think we're good. Um, thank you everyone for attending. And thank you, Dr. Lepre, for telling us all about the Earth's magnetic field. I learned a lot too. So thank you for everyone who attended. We will be doing our next live stream this Thursday. It will be on the Kilauea eruption that happened 2016, I think. Let me just check the time. I forget. I think it's at 2 p.m. we're doing it. So, so 2 p.m. on the 2018 Kilauea eruption. You can click the same link that you used to get to this one, and hopefully we'll see lots of you on Thursday. So thanks for joining us.